as I said, only these 3 sections about the exponential and logarithmic functions. Okay, so from algebra we know that the exponential function has 2 possible shapes. Can anyone give us an example of an exponential function? Please don't be afraid to be wrong. When we are wrong, we learn. So just give me an example of an exponential function if you remember any. Anyone, please? Anyone, please? Why do we call it exponential? Can anyone give us an example of an exponential function?
Like x cubed plus.
Careful. That is polynomial, right? If we say x cubed plus 2x squared plus, I don't know, 4, this is polynomial.
Would it just be x squared?
This is x squared is only polynomial. So let's review this. It's okay. As long as I know that where we have to start, that's fine. When we say exponential, it means the power is the variable. That's why it's called exponential, because x is the power, not the base. X to the third has base x and power 3. No, the power is the exponent. So the general case is a base raised to power x. But there are restrictions for this base. So the base must be not 0, must be not 1, and it cannot be negative. Well, what can it be? Okay, so there are 2 options for A. A could be either strictly greater than 1, not 1, or tiny, between 0 and 1. So please remember, we call this exponential because the variable is the exponent. This is a constant. This is given. It's a number. So we have 2 shapes. When the base is greater than 1, for example, can anyone give us an example with a base that is a number greater than 1?
2.
Yes, 2 to the x is a very good example of an exponential function. Awesome. So when the base is greater than 1, here's how it looks. This is a to x when a is greater than 1. And this is what we've been seeing and confronted with, in the last 3 years. That's why when they said 1 person or 2 people get sick now, in 3 days, 10,000. And then in 3 more days, 100,000. So that was the pandemic we experienced. And they said, okay, let's flatten the curve. Can we flatten the curve? That's what they meant. Try to stop it from going up like that so fast, and the number of people getting sick. So this was an example of what we experienced. Okay, a base greater than 1. It was going up fast, so fast. Okay, there is a second shape, this one. Can anyone give us an example of an exponential function with a base between 0 and 1, like 1/2, 1/3, and so on and so forth? Can anyone give us an example so I can put it here? And then graph it. I will graph it. Notice that when x is 0, the number, any number raised to 0 is 1, right here. So it crosses at 1. Can anyone give us an example with a base of an exponential function with a base 1/2, 0.2, 1/16, 1/8, but create the exponential function so we can see it.
1/2.
But not 1/2, but 1/2
X.
yes, 1/2 raised to power x. Very good. This with a base less than 1, still positive, not 0, not 1, not negative, is identical, has identical shape, but decreasing on all its domain. So this is still a to x, but this time a is tiny. How do we call this line for both shapes? How do we call this line? It doesn't matter if it's for this shape or for this shape. Horizontal what?
Asymptote.
Thank you very much. So y equals 0 for both shapes. So notice that this is pure exponential function. How will an exponential function not pure look like? For example, something like this. This is not pure. It's a combination of different things. This is pure, just base to x. This is pure, just base to x. So y equals 0 is a horizontal asymptote for the pure ones. These have other asymptotes, horizontal asymptote. This will have a different horizontal asymptote. But for the pure ones, just base to x when a is between 0 and 1 or greater than 1, has a horizontal asymptote at 0, y equals 0. Okay, good. So now if we are asked, for example, limit as x approaches infinity from 1/2 to the x, what will you say? Look at the graph. Look at the one that represents 1/2 to the x and tell me what to write as the limit. So this part was the algebra that you've seen before, but this is the calculus that we discussed. So we're applying calculus now. So what is the limit as x approaches infinity from 1/2 to the x? By looking at the graph, you will say,
Is it negative infinity?
so careful, 1/2 to the x when x approaches infinity.
Zero.
Thank you. Horizontal asymptote. What if I say now the limit as x approaches negative infinity for 1/2 to the x? Looking at the graph, what will you say? Anyone, please?
0.
Let's do this again. X approaches negative infinity from 1/2 to the x.
Is it infinity?
Yes. Very good. Awesome. Infinity. Great job. Thank you. Good. Now, let's take a look at a few applications. We do have one application, if you remember, the accumulated value, P, 1 plus R over N raised to NT. Accumulated value, principal, annual interest rate, number of times we compound interest, T number of years. We've done this before. If you remember, when we started, I also said there is something, so this is compound N times per year. But also I said a long time ago that there is something called continuously compounded interest. And that is still the principal. Now the base is E to RT. continuously compounded interest. So there are two formulas again. Interest compounded n times per year that we discussed in chapter R. But this one is continuously compounded interest, where the base is E. So we have two special exponential functions. Two very special ones. One is the one with the base 10. And this is called common exponential function. And there is the second one called natural that has base E. So number 2, f of x equals e to the x. And this is called natural. And they are so special. I'm going to share my screen. Where are you guys? I lost you. I found you. So they're so special that, look here. See, we have to activate them with the second key, 10 to the x and e to the x. So if I want to determine second, 10 to whatever, second power, I know it's going to be 100, so we get 100. If I want to determine e to a power, let's say power 3, then first of all, let's identify what e is. Very simple to find e. It's right here at the division symbol. If you just want plain e, you can use this. You can still use e to a power and just put power 1. And you'll still get the same number. As you see, 10 and e have both the same shape because the base is a number greater than 1. So 10 and e is 2.71828 blah blah blah. It's an irrational number. So they are so special, these two, that they have their own key in the graphing calculator. Second 10 to the x, second e to the x. Common exponential function, natural exponential function. So the continuously compounded interest formula uses the base that is e, which means it's a natural exponential function. Okay, I would like us to look at a problem. So before we continue with more rules, I thought I opened my book. Where is the book? Here it is. Yeah. Okay. So I would like us to directly go to a problem. I'll come back to these, or we can just select from here. Let's select from here first. Yeah, 9 through 16. So 9 through 16. So let's see what they're asking us to find. An initial investment amount P, okay, principal. An annual interest rate, of course, R, and the time T are given. Find the future value, the accumulated value, in other words, of the investment when interest is compounded annually, monthly, daily, and of course continuously. Then find something called the doubling time for the given interest rate. So we have to go through all these, A through E. So I'm ready for you to choose, or I will. 1. Yes, which one?
11.
11. So we want to look at 11, and this is on page 203. Let me copy it and stop sharing. So we have the principal, 75,000. We have the interest rate 4.5%, which we know we have to change immediately, and T equals 3 years. Okay. So we want, I need to copy this annually. Fine. Then monthly, daily, and they also want continuously, and find doubling time. Perfect. Thank you for the pick. So now let's take a look. For these, we have this formula. Nothing new here so far. The formula that we've been using all along. However, for continuously compound interest, we have a different formula with the exponential function. That's why we couldn't talk about it till we got to the exponential function. The doubling time, I'm going to have to explain. So we're going to get to that in a minute. So I'm going to copy the formula for this. So this is A equals the principal, 75,000, 1 plus. Can anyone tell us how to write the interest rate? Because I cannot use 4.5%. How do I write it?
0.045.
Awesome. Thank you very much. 0.045 divided by annually. How much is N for annually?
36.
1. Every year, annually. How much is N? No worries, no worries. How much is N for monthly?
12.
Very good, awesome. How much is N for daily?
365.
Yes, we normally use 365. Awesome. You know me, I'm not going to do this 3 times. Oh no. I'm going to put this in the graphing calculator, and that is the power here is N times T, which means 3x. I'm going to plug in why I write x. I should write N, but x is in the calculator, so it doesn't matter. You can write N or you can write x. It doesn't matter. But in the calculator will be x. So I will use the table. I use 1, then I will use 12, then I will use 365. So I will have A of 1, A of 12, and A of 365. I'm not going to do this step by step. You're missing a lot. You may introduce a lot of error if you do that. So please don't. This is so much easier, please. So in y equals, clear if you have anything else, and put in the function as we have it here, as we see it, parentheses, 1 plus 0.05, I'm sorry, 0.045 I meant, divided by x, it should be n, but I don't have that, power, I like parentheses, so I'm going to have 3x, and close. Now all I have to do is go second in table. All I need to plug in is 1, then 12, and then 365. Don't work hard. There is no need to do that for this. I have to highlight it because I need 2 decimal digits. When it comes to money terms, we need 2 decimal digits. So we get 85,587.46. Next one, down. The next one is 85,818.59. And then the last one, 85,839.54. And it's done in 1 step. Well, when it comes to one time, one calculation for the continuous, I can just simply write A equals 75,000 times E to R, which is 0.045, times T, which is 3. This is one calculation. Since it's only one, I can do this. 75,000. Yes, I know. I'm not afraid of my students. Why are they? I'm just kidding, of course. But I'm not afraid of my students seeing my screen. I have nothing to hide. So 3 times 0.045, close, and enter. So I got 85,840.26.